All right, guys, let's rock. We're going to work through some motion problems. Remember, this was a crazy path in class. We're going to work through as many problems as we can. Remember that the answer will be on the next slide, so hopefully we'll be able to work them all out. All right, so we're going to go ahead and go through these questions. If you need to read the question, go ahead and pause it so you can read through it. I'm going to jump into these questions right away just so that we can get through as many as we can, as quickly as we can. And here we go. So we've got that it takes 10 seconds to walk 8 meters to the fountain. He stops to drink for 5 seconds, and then he returns to Mr. Bywater's classroom in 3 seconds. All right, so the first question is, what is Toby's total distance? So it says that he went 8 meters over to the water fountain, and then he went the 8 meters back to Mr. Bywater's classroom. That would mean a total distance of 16 meters. The second question is, what is his final displacement? Well, remember, displacement is the distance from your starting point to your ending point. He started and ended at Mr. Bywater's classroom. If that's the case, it's the same place, and the distance between those 2 points is 0 meters. So 16 meters and 0 meters. Normally we should have a direction for displacement, but if it's 0, there ain't no direction. Now you will notice that our answer will be at the bottom right-hand corner of the next slide. 16 go and 0. Whoop, there we go. All right, so we've got that it's going from rest to 3.7 meters per second in 5 seconds. So I've got a velocities, I've got a time, and it's asking for acceleration. So we're going to use acceleration equals the change in velocity over the change in time. Change in velocity is final velocity minus initial velocity, and change in time is just that 5 seconds there. And the final velocity was 3.7 because that was at the end, and subtract the initial velocity, which it says it went from rest, so that would be 0 to 3.7. And then divide by 5, and when we work that out, we should get 0.74, and that should be it, 0.74 meters per second squared. The top was in meters per second, the bottom was in seconds. That should give us meters per second squared. And check the next slide, and look at that, it was 0.74. Awesome. So next one here, the position versus time graph. And the first question is, what is my speed as I leave home? Remember, speed is the slope. Okay, now the slope is actually the velocity, but velocity and speed are the same if it's going in a straight line, which is what's happening here. So straight line, we can use the slope, which means we need 2 points. We're going to do y2 minus y1 over x2 minus x1. And so we've got a point here, which is going to be 3 minutes, but I do want it in seconds. So that's going to be 180 seconds. And then the x-axis here is 600, or y-axis, so 180, comma 600. And then down here it's 0, 0. And so we put those together. We go y2, which would be 600, minus y1, which was 0. And then x2, which is 180, minus 0. And so we do 600 divided by 180, and we end up getting 3.3 meters per second, right? It was meters over on the left-hand side, the y-axis. This was in meters, that was in seconds, so it should end up giving me meters per second. Now the next question is, what happens between 3 minutes and 4 minutes? So that's here and here, and you'll notice that I stay at 600 meters, which means I stay at rest. Now you might say stay at rest or stopped at a stoplight, any of those things, but the position isn't changing. Now the last question is, how long did I stay at Lulu's? Well, right here it says Lulu's is 1 kilometer from my home. So 1 kilometer is 1,000 meters, so that's this right here. So I was at Lulu's from this point to that point. That's all at 1,000 meters. So it looks like 1, 2, 3, 4, 5 minutes. So therefore, we should have 3.3 meters per second, stay at rest, and 5 meters. So here we go. Ta-da! 3.33 at rest and 5 meters. On to the next question. So let's see. He's moving off in a straight path, constant speed, 2.3 minutes of flying. So I know that my time is 2.3 minutes, which I'm going to go ahead and turn that into seconds right away. So I'm just going to go 2.3 and then multiply by 60 because there's 60 seconds in a minute, and I get 138 seconds. And it says he's surprised to see the drone has traveled 4 kilometers. What is the average speed? Now remember, average speed is distance over time. So the total distance there was 4 kilometers, which is 4,000 meters. And then we're going to divide by the time, 138 seconds. And when we divide that, we should get 4,000 divided by 138, and we get 28.98. So we're going to call that 29 meters per second. There we go. And we check the answer. Ta-da! 29. All right, next one. We got a battery-powered car rolling along the ground with the speed of 94 centimeters per second. So we're going to go ahead and write that down. So 94 centimeters per second. I really do want that in meters per second. So there are 100 centimeters in 1 meter. So I'm going to divide by 100, and I'm going to get 0.94 meters per second. If we're able to roll along the ground for 8 minutes, how many meters would it have traveled? So time is going to be 8 minutes. But again, I want that in seconds. So I'm going to go 8 times 60, which will be 480 seconds. And so now I've got speed and time, and I'm looking for meters. So I know that my formula then is speed equals distance over time. I know the speed, which is 0.94. I know the distance, well, I'm looking for the distance, and then the time is 480. Now to solve for D, I just need to multiply both sides by 480. 480. That's what I said. So multiply this side by 480 as well. And 480 times 0.94 is going to give me 451.2 meters. So about 451 meters. And ta-da! 451. Moving on to the next one. We got another graph here. Actually, the same graph as last time. This time it's asking some different questions. What is my total distance traveled? Well, I started at 0. I went all the way up to 600. I kept going up to 1,000. And even after that, I kept going up. I went all the way up to 1,200 meters. And then I went all the way back from 1,200 meters. So remember, distance is the total path traveled. So it's going to be that 1,200 plus the 1,200, which is going to be 2,400 meters. All right. Now the next question is, what is happening at t equals 12? Okay, well, t equals 12 is right here. Now, hopefully what you'll see is that I was moving away from home. My distance from home was getting bigger, and then I started moving towards home. Now, what that means is that at that point, I turned around and started going the other direction. All right. Next question is, what is my velocity for the last 2 minutes? All right, well, velocity, remember, is the slope of the distance versus time graph. This one right here is at 12 minutes, 1,200 meters. And then this one is 14, 0. Now, I'm going to go ahead and do the slope. The slope is y2 minus y1 over x2 minus x1. So for the y2, I'm going to put in the 0 there. And then for the y1, I'm going to put in the 1,200. And then I'm going to divide by the x2, which would be 14. But I do want it in seconds. So I'm going to go ahead and do 14 times 60. And that's going to be 840. And then minus x1. And x1 was 12. So I'm going to do 12 times 60. And 12 times 60 is 720. And so when I put those together, I'm going to end up having negative 1,200 over 840 minus 720, which is 120. You could have got that from the fact that that's 2 minutes there. 2 minutes is 120 seconds. I divide and I get negative 10 meters per second. Now the negative is important because remember, velocity has direction, and the negative means that I'm going back towards my home. The positive was going away from home, the negative is back towards the home. So I should have 2,400 meters. I turned around and negative 10 meters per second. Let's check. And there we go. 2,400 turning around and 10 meters per second. All right, so in this one, it says James's car can travel at 2.8 meters a second and can go around the track in 16.4 seconds. And then for James' 2 car, they only give us the speed of 2.1 meters a second. But we do know that they're going around the same track, which means they must be going the same distance. Even if their speed and time are different, the distance must be the same. And so because I know stuff about James's car, then I'm going to take that 2.8 meters a second and the 16.4 and see if I can find the distance, which is going to help me with James number 2's car. So I know that speed equals distance over time. The speed was 2.8, and then the distance is what I'm looking for, and the time was 16.4 seconds. And so in order to solve for D, I'm going to take that 2.8 and multiply by 16.4, and I get a distance of 45.92. The speed was in meters per second, the time was in seconds, so my distance is in meters. Now, since I know James number 2's car does the same thing, now I can do speed equals distance over time for James number 2. And so James number 2, his speed is 2.1. His distance is the same because he's going around the same track, so 45.92, and then divided by the time. Now this one's going to be a little bit harder. I need to move the t off the bottom. Remember, anytime your variable's on the bottom, you got to multiply by that first. That's going to leave me with 2.1t is equal to 45.92. So then I'm just going to divide both sides there by 2.1, and I'm going to get an answer of 21.9. So t equals 21.9 seconds. Now that kind of makes sense because he was going slower, so it should take him longer than 16 seconds. So 21.9, that doesn't mean it's right, but it does mean it's reasonable. Let's go ahead and check. 21.9, there it is. All right, so now we're back to Toby. Remember that question about Toby before he was walking to the water fountain? I don't know if you remember, but before we said that the distance was 16 meters and the displacement was 0 meters. That's going to be helpful because here it asks for Toby's average velocity and his average speed. Now, velocity, remember, is displacement over time, and so the displacement was 0, and then the time doesn't really matter, right? The time can be anything, but 0 divided by anything is 0, so the velocity is going to be 0 meters per second. Now the speed is going to be a little bit more work, but that's okay. Speed, remember, is distance over time, so the distance traveled was 16 meters. Now the time, it took him 10 seconds to get there. He paused for 5 seconds at the water fountain, and then it took him 3 seconds to get back because he forgot to tell Mr. Bywater that he was leaving the room. So 10 plus 5 plus 3 will be 18. So 16 divided by 18, that's the same thing as 8 over 9, which is 0.888 repeating. So about 0.89 meters per second. And that's going to be our speed. So there we go. 0 velocity. 0.89 meters per second. Ta-da! That's what we got. We're moving along. Now we got a graph. Ooh, this one is a different graph. This one is a velocity versus time graph. Look at that. All right, so let's check this out. The first question is, what speed does the elevator travel for the first 6 seconds? So here's the first 6 seconds right here. And you'll notice, remember, speed and velocity are the same thing if they're moving in the same, if it's a straight line. Now here the velocity is constant at 4 meters a second. That means the speed is also going to be 4 meters per second. All right, the question then is what happens at t equals 6 seconds? Well, that's right here. Well, it was going 4 meters a second, and now it's going 10 meters a second. So what happened? Well, it went from 4 to 10, which means it sped up instantaneously. So let's just say that it accelerated instantaneously. There we go. The last question, how high does the elevator travel in the first 12 seconds? So how high does the elevator travel in the first 12 seconds? Well, that's from this point right here all the way to that point. There's my 12 seconds. Now, there's a couple ways to do this. You could use some formulas, but I'm going to encourage you to use what we talked about in the video for the graphs, which was that the distance or displacement, the displacement is the area under the velocity versus time graph. Okay, so what we need is the area. So I'm going to take this right here. The height is 4 meters a second, and then the width is 6 seconds. So I multiply 4 by 6, and I get an area of 24 meters for this. And then I'm going to do the same thing here, but this one goes all the way up to 10. So that one has a height of 10, and then a width again of 6. So 10 times 6 is 60. So that means that this area right here is 60. So I add up all those distances together, and I get a total of 84 meters. So that's how high it went, 84 meters. 4 meters per second, instantaneous acceleration or sudden acceleration, and 84 meters. Whoop-a-doo-doo. Yeah, we got it, baby. Moving on to the dancing dolls. Yep, that was a mistake. So let's see. It says, in one instance, the doll moved at 35 centimeters a second forward for 5 seconds, spun around for 1 second, and then moved sideways to the right at 25 meters a second for 3. So I'm going to actually draw this out. So it went straight at 35 centimeters per second for 5 seconds. Now, that's a speed and a time. The question here is going to ask me for the distance traveled. So to get the distance traveled, I'm going to go ahead and say that speed equals distance over time. Now, the speed was 35 centimeters a second, which remember there's 100 centimeters in a meter, so 0.35 meters per second is equal to the distance divided by the time. And so now I just need to multiply both sides by 5, so 0.35 times 5 gives me an answer of 1.75. So the distance is equal to 1.75 meters. So I'm going to go ahead and label that here, 1.75, and that's in meters. And then it turns to the right, and then it travels at 25 centimeters per second, which is 0.25 meters per second for 3 seconds. Again, we'll go speed equals distance over time. The speed is 0.25 equals the distance over the time of 3 seconds multiplied by 3, and we get a distance of 0.75 meters. So we'll go ahead and label that one. So at this point, I have a total distance. I can add those up because the distances just add up all the paths. 1.75 plus 0.75, and I'm going to get a distance of 2.5 meters. Not too bad. Now here, it wants the magnitude of the displacement. Now magnitude, a lot of people are a little bit confused about this. Magnitude is just the value. Okay, so it's just the number. Remember, displacement is a vector, so it should have a magnitude and a direction. Well, the magnitude is just the number, the value. Okay, so that's all we're looking for here. It's just saying we don't have to worry about the direction. Now, remember the displacement is from the starting point to the ending point in a straight line. Now, hopefully you're looking at that and you're saying, oh, that is a right triangle. I can solve for that. I can do 1.75 squared plus 0.75 squared. Now, if you don't know where that's coming from, remember this is a right triangle, so we can do a squared plus b squared equals c squared. So that 1.75 squared plus 0.75 squared should give me c squared. Now, if I do the math there, I get 3.625. Now, remember, that's still equal to c squared, so I am going to need to square root my answer there, and I should get an answer of 1.9. So c equals 1.9 meters. that is the magnitude of the displacement. We're not going to worry for now about the angle. Maybe someday we'll do that in the future. All right, there we go. So 2.5 and 1.9, and yeah, baby, that's exactly what we got right here. Now, the next question asks for the average speed and the magnitude of the average velocity. Remember, speed is equal to the distance over the time. In the previous one, we found that the distance was 2.5 meters, and then the total time is 5 seconds, 1 second for the spinning, and then 3 seconds, so that's going to be a total of 9. So we go 2.5 divided by 9, which is 0.28 meters per second. Now, please make sure that you do this, that when you find the average speed, you get the total distance and divide by the total time. You cannot just average these two speeds, because averaging the two speeds, you do those speeds for different amounts of time, right? It's like you're taking a long trip from here to Dubai, and for most of the trip, you go 120 kilometers per hour. And then at the very end, you have maybe 5 minutes of traffic, and so you're only going about 10 kilometers per hour. Now, you just traveled 120 kilometers per hour for 5 hours, and then the last 5 minutes you were going pretty slow. Does that mean that the average speed is 120 plus 10, which would be 130 divided by 265? Is your average speed 65 kilometers per hour? Well, absolutely not. That doesn't make any sense, because you spent so much time going this speed, your total average speed should be closer to that. And you will notice that the 0.28 is close to this 25. That's because when they were spinning around, they were actually at rest for a second. And so therefore our answer is going to end up being a little lower than the normal average between the two. Okay? So hopefully that's what we got for the speed. Now the average velocity, remember velocity is displacement over time. So velocity is displacement over time. The displacement we had, which was that 1.9, and the time is still going to be 9 seconds. And so when we do the 1.9 divided by 9, we should get 0.21 meters per second. There we go. So those should be our answers, 0.28, 0.21, and yes, they are. All right, now this is actually our last question. You may have seen the answer on the very first video, but let's go ahead and talk through it anyway. First question, at t equals 18 seconds, what is the acceleration of the elevator? Now, acceleration from a velocity versus time graph is the slope. So we're looking at this time, 18 seconds, we're going to find the slope of the line that matches that 18 seconds there. All right, remember that slope of velocity versus time is acceleration. And you can do that because the change in y, it would be in meters per second, and the change in x, so remember that slope is change in y over change in x. Change in y would be meters per second, change in x would be seconds. Divide those two, and you get meters per second squared, which is, by the way, acceleration. So I'm going to go ahead and do that delta y. I'm going to pick off a couple of points. So the first one is going to be 16 comma negative 16 there. And then this one is going to be 22 comma 0. And then we'll go ahead and put that together. So y2 would be 0 minus y1, which was negative 16, over x2, which would be 22. I'm using this as my second point. This is my first point, minus 16. And so I go 0 minus negative 16. Remember, minus a negative is positive. And then I do 22 minus 16, which will be 6. So I go 16 divided by 6, and that would be 2.7 meters per second squared. So there we go. We got our acceleration during that time. Notice that the acceleration is positive. That's because the velocity is getting more and more positive. Note that the velocity is 0 at this point, which means that it's at rest. It's getting closer and closer to rest, which means it's slowing down, but the acceleration is positive because we had a negative velocity that was becoming more and more closer to the positive region. Okay, the next question is, what happened to the elevator at t equals 14 seconds? Well, here's 14. Before that, it was at rest, and then after that, it started speeding up. So at 14, we could say a couple of things. You could say it's speeding up, or you could say that it's dropping. Either one of those would be acceptable. You could even say that it starts dropping and speeding up as it does. Okay, there is some acceleration there, but it will speed up as it goes. All right, the last question is, what is the maximum speed of the elevator? Now remember, speed, instantaneous speed and instantaneous velocity are the same, except velocity has direction. Speed doesn't care about the direction. So we'll notice that up here at the top, the biggest positive velocity is 10, but down here, the biggest negative velocity is 16. So what that means is that the largest speed is actually 16 meters per second. Yes, it's in the negative direction, but that's the fastest it goes, which makes sense. As it does that drop at the very bottom, as it starts to slow down, that's the fastest it's going to go right before it starts slowing down. All right, that's it. We've answered all the questions in this. I hope that was helpful. And please do use this if you need it to help you finish the assignment. We'll see you next time.